All right, folks, welcome back. We're ready here to begin step 3 in the 12-step method. We're moving right along here. Again, this is off of page 146 of Szabo and Ostlund. We're on step 3. We completed step 1, which was reading in the data and preparing the Gaussian approximations to the Slater functions. And then step 2 we've completed, which was calculating all the 1-electron and 2-electron integrals. So we are ready to move on. Step 3 is a linear algebra step. The ultimate outcome is to prepare a change of basis matrix that will apply to the Fock matrix within the self-consistent field algorithm. That'll then allow us to solve the transformed Hartree-Fock equations that are kind of I think they call them a pseudo eigenvalue equation. So let's get going on that. Let's highlight this so we can see it up through step 3. Let's make it visible. A few steps involved here. You recall our overlap matrix, our S matrix. Let's go up here and take a look at it. It was up here, and it is not orthogonal. It has off diagonal values, so it is not orthogonalized, and we need to work in a basis where it is orthogonal. So this is going to help us to do that. So we're going to diagonalize this overlap matrix, and just going to use the equation here out of Szabo and Ostlund. This is equation 1.105 in the Math Chapter 1 at the beginning of the textbook. We'll use this equation, and he puts a little caveat in here in case the two diagonal elements are the same, which they are sometime. Then instead of having the computer deal with the arctangent of something over 0 or the arctangent of infinity, we'll just set that equal to pi over 4. Okay, that will solve the problem. So we'll take pi over 2 divided by half, get pi over 4 if that happens to be true. So that gives us our rotation angle. We will find the orthogonalized S matrix by just taking the matrix of eigenvalues. We'll use Mathematica's handy eigenvalue finding routine here. So there's the diagonalized S matrix. And then further, we want to calculate a diagonalizing matrix, and then finally a change of basis matrix. So we'll calculate the diagonalizing matrix and its transpose. And in the textbooks, they do this with a little superscript. Looks like a little cross, or it's actually a little dagger. I call it U dagger here. And that represents what they call the adjoint. And when I got into this, I found out what they're talking about adjoint isn't what I remember adjoint from my linear algebra class. I remember adjoint as being kind of a transpose of a cofactor matrix, and that's not what they're doing here at all. Apparently, what I learned in linear algebra is more properly called the adjugate, and we're not doing that here at all. The adjoint here is simply taking the transpose of the matrix and then taking the complex conjugate of each element of the matrix. But in this case, we're dealing with real matrices, so the complex conjugate is the same as the original matrix, so it's really just the transpose. But I called it U dagger here, so it just looks like the formulas in the book. So I'll use my rotation angle that I calculated, and from that I can calculate the diagonalizing matrix U. It's equation 1.104 in Ostlund. And then U dagger is just the transpose here, since it is a real matrix. So calculate those, U and U dagger. I want this to be normalized, so I normalize by dividing by the magnitude. They call that the S1/2 matrix. That's equation 3.26. And then what I really want is this change of basis matrix to apply later to the Fock matrix within the algorithm. This is using equation 3.169. This is canonical orthogonalization. I think most of the time you can use what they call symmetrical orthogonalization, or a person could use the, to me, more familiar Graham-Schmidt orthogonalization, but they do the canonical orthogonalization, so we will too. So that's equation 3.169 that calculates our X matrix here that we will be using later. So we need that, and those values should correspond nicely to what we see in the textbook for the correct values. Step 4 is very easy. Let's highlight it here. It's just to get an initial guess for the density matrix. So make a guess for the density matrix. It's called P in the textbook. And a number of things a person can do here is, for an initial guess, and for these simple systems, your initial guess really doesn't matter. One thing is as good as another, I suppose, if you don't get too wild. But traditional thing is just to assume the electrons are all uncoupled. One electron doesn't see another electron, and just fill the density matrix up with zeros initially. This makes your initial Fock matrix look like the core Hamiltonian. That seems to be a fairly traditional way of starting things off, and if that doesn't work, then you try something else. But for this simple system, it works fine. So we'll just zero out the density matrix. We'll call it P here, set it up for zeros. And I also need to initialize the G matrix. This is the effective part of the electron potential, called the G matrix, and set that up with zeros as well to start it off. Then we'll calculate it later. So that's done. We've made an initial guess to start the iterative procedure, and we've initialized our G matrix so we can start adding things to it, starting with 0. So that's it. That's probably a good place to stop on this video. We are ready to begin the iterative part of the algorithm. I'm trying to keep up here with the table in Szabo and Oslin, so my numbers agree with the way they get them. So I started off here by setting the iteration number to -1. So once I get in, it's iteration 0. It seemed kind of weird, but I wanted my numbers to be easy to compare with the numbers in a textbook. So that's what I did. So if you have Szabo and Oslin text, turn to page 176 and look at table 3.5 as we run through a number of iterations, and you should see us close in on the converging electronic energy of the system. So let's stop there. When we come back in the next video, we'll actually be starting the iterative part, the self-consistent field part of the algorithm, which is kind of fun. We're going to take it a step at a time and then watch it slowly converge. So I'll see you in the next video. Thank you. Bye-bye.